Oh, great. Well, buenos días, buenas tardes. Gracias por acompañarnos hoy. Good morning, good afternoon, everybody. Thanks for joining our webinar. My name is Joe Amador. I'm Vice President of the IAPG Houston Board, and will be your moderator today. I'm joined by fellow board member Mariano Clerici, who will be helping with the Q&A session, as well as by our speaker, who I will introduce shortly. We're pleased to be hosting this webinar as we continue our effort to present industry themes relevant to the regional oil and gas sector. Today, we will discuss surfactants for enhanced oil recovery in unconventional reservoirs. So before we begin, let me provide a brief description of the IAPG Houston. We were incorporated in 2002 as a nonprofit organization to promote the sharing of knowledge in the energy space between the US and Argentina. We share in the principles of our Petróleo y Gas. We are run by a board of about 15 professionals who provide our time on a pro bono basis. We organize virtual events, such as this technical webinar, and in-person conferences where we host company CEOs, Argentine ministers, provincial governors. We have even hosted 2 of the country's recent presidents. We also offer networking opportunities such as cocktail parties and golf tournaments. Our next big event will be our 4th Shale in Argentina conference, where we will focus on progress in the development of the Vaca Muerta. The event is scheduled for September 12th here in Houston, so please save the date and look for upcoming details. Some 20 years ago, we began a scholarship program for Argentine professionals interested in pursuing graduate degrees in energy. Today, we are proud to have over 20 scholars we have sponsored by way of our own Claudio Manzolillo program, as well as via our cooperation agreement with the Fulbright US student program. Program details can be found on our website. Funding for our organization comes by way of generous contributions from companies like Chevron, Pan American Energy, Shell, Tenaris, ExxonMobil, Schlumberger, Equinor, United Airlines, and GNP Neuquén. I see many of you here today work for these companies, so I would like to extend a special muchas gracias for your continued support. We encourage you to follow us on LinkedIn, visit our website, if you would like additional information regarding the organization or how to become a member or how to become a sponsor. Some logistics for today. We are recording this event, so please be cognizant of that. The recording will be available for those who registered. We will send you a link shortly after the event. Our presenter will kick off with a approximately 45-minute presentation, and we'll take questions after that. Please submit your questions through the chat function or via the Q&A function, which you can find at the bottom of your screens as you are all muted. Feel free to send them in Spanish. We will translate them. We will target wrapping up in about 1 hour, but our presenter has generously offered an additional 30 minutes if needed to try to ensure everybody's questions are answered. Ross, go to the next page. Today, we are pleased to be hosting Ross Harkrider, Director of Operations at Alchemy Sciences, where he designs, formulates, evaluates, and does field execution for new products to maximize oil recovery. Ross has 20 years of experience in the industry. He began his career in 2004 at Schlumberger, now called SLB, as a field engineer in the Gulf of Mexico. He also worked at various other companies, including BHP Billiton, before joining Alchemy Sciences in 2017. I believe that covers the intro. Ross, take it away.
All right, thank you very much, Joe. I'm excited to be here, and I appreciate the opportunity to speak to the group today. I hear there's a lot of buzz around this subject and a lot of interest and excitement, so I'm excited to be here and present this subject for you today. As Joe already mentioned, what I want to talk about today is how can we increase production in unconventional reservoirs utilizing customized surfactants. Unconventional reservoirs have been a pretty tough challenge for the industry. We have come a long way and we have learned a lot over the last 20 plus years, but we're estimating that for every barrel that we produce out of a given formation, we are still leaving 9 barrels in the formation. 10 or less % we are getting out of these unconventional formations. And a lot of times we're finding that they're becoming uneconomical. And so the industry has got to do something to make these reservoirs more economical. The other thing that we are observing is that the industry has more or less reached a plateau with the fracturing and stimulation technology. We've done a lot, we've made a lot of progress. How much sand, water, what kind of sand, perf spacing, well spacing, lateral length, those are all things the industry has really been focused on over the last 20 years in these unconventional reservoirs. But now we're seeing that we make a few adjustments and we're only seeing very small improvements in these reservoirs in this area. And so the industry has got to move to newer technology, things that can get more production out of these very challenging reservoirs. So today, speaking about surfactants, how can surfactants do this? Okay, we know surfactants have been in the industry for a long time. This is nothing new. And I think if anyone is familiar with surfactants, they might be familiar that there are basically 2 mechanisms that a surfactant targets within a reservoir. The first one is interfacial tension, or IFT. There is a surface tension or an interfacial tension between oil and water, or oil and gas, or water and gas that is naturally there. And as you're able to lower the interfacial tension, it can allow the oil to flow more freely through the system, thereby potentially increasing production. The second mechanism that many of you may be already aware of is wettability alteration. Every reservoir has a natural tendency for a type of liquid to be attracted to the face of that rock. If water is naturally attracted to the formation, this is called a water wet rock. And if oil is naturally attracted to the formation, this is called an oil wet rock. Carbonate reservoirs tend to be more oil wet. Sandstone reservoirs tend to be more water wet. And if you have reservoirs that are somewhere in between a carbonate and a sandstone, you have a mixed mineralogy, then you might have a mixed water wet system. And so what can surfactants do for us? Understanding that system is really what I want to speak to today. Okay, so I want to take a deeper look at what is a surfactant, how does it work, how can surfactants increase our production? We'll take a small brief look at the formulation process, and then we'll look at some samples from the lab and the field, and then we'll wrap up with any questions that you might have. Okay, so what is a surfactant? A surfactant is basically 2 components, a head and a tail. The head part is naturally attracted to the water portion. It is water soluble, or also known as hydrophilic. The tail portion is going to be naturally attracted to the oil substance. It is oil soluble, or called hydrophobic. As we move into the 2 areas that surfactants can impact, interfacial tension and wettability, surfactants want to move to the interface of whatever substances we're looking at. So if it's interfacial tension, we're working with 2 liquids here, or the oil and the water. The surfactant wants to move to the interface of that oil-water interface, thereby interacting and impacting that interface between oil and water. If it's water and the rock surface or oil and the rock surface, again, the surfactant wants to move to that interface, thereby interacting with that interface and hopefully, potentially changing how that interface reacts. If you know anything about surfactants, there are thousands of different types of surfactants, which can make the world of surfactants kind of daunting. So many different types of surfactants. How do I choose a surfactant? But basically, surfactants can be categorized into 4 big areas. We have non-ionic surfactants, anionic, cationic, and amphoteric. Okay, the first mechanism that we're looking at here today is interfacial tension. How exactly does interfacial tension help increase production, and what is interfacial tension? The chart here on the left, on the x-axis, is surfactant concentration, and on the y-axis, we have interfacial tension. If we have 2 liquids, oil and water, or in some cases, gas and water, or even gas and oil, the surfactant, when surfactant is added to that system, the surfactant will move towards the interface between those 2 substances and will begin to saturate that interface. And as it begins to saturate that interface, we begin to move down on our graph here. Eventually, we're going to reach a point where the interface is fully saturated. This point here is called the critical micelle concentration. So as additional surfactant is added, the remaining bulk can no longer go to the interface because there's not enough room, and will begin to create these micelles in the bulk. What's important about this here and understanding where the CMC point is with your given system, because again, interfacial tension can change the actual value depending on what you have. If you have water oil, water gas, gas oil, the kind of oil, the kind of water, all of that interfacial tension can change depending on what your substance is. Then also your surfactant. What kind of surfactant do you have? So your CMC point can change depending on all those variables. The point that I want to make is that as we understand where my CMC point is, if we begin to add more surfactant to a system, we may not be continually to decrease the IFT. And so now you're adding maybe possibly unnecessary surfactant. You may be even spending money that you don't necessarily need to spend if you're adding too much surfactant. Likewise, on the flip side, if you're on the left side of this line, you might be under-treating your system and you may not be adding enough. And so how do we get there? We've got to understand the system. We've got to understand the surfactants. Okay, so how does surfactant help increase our production? Okay, from a high level, I think it's we're pretty able to understand that it's going to help my oil flow more freely through the system. But breaking it down to kind of an equation to really see, okay, how does it actually work from a mathematical standpoint? So I've got the capillary number equation here on the right. And the capillary number is basically the ratio of the viscosity forces between the substances that you're working with, oil, gas, water, and the capillary force and the interfacial tension that you have there. So as we move down the interfacial tension line over here on the left, we're decreasing our interfacial tension. In this equation over here, our interfacial tension is in the denominator. So as this number goes down, our capillary number will begin to increase. So my chart here on the x-axis is my capillary number. So as my IFT goes down, my capillary number will increase. And on my y-axis here, I have % oil recovery. So as you decrease your IFT, you have the potential, it doesn't mean you will, but you have the potential to increase your recovery in your reservoir. Okay, this might be an image that many of you are familiar with. This is basically just an image at the pore scale of a rock sample. We're in the nanometer scale here. And so what I want to show here with this image is that we need to understand our system. I mean, here we have a real life example from an SEM machine. We've got our gray material. This is grain, inorganic, which is often tends to be water wet. We then move over to the green spaces here. This is organic matter, which can be kerogen or it could be crude oil. And then we have our pore spaces. Okay, so the point from this image here is that we need to understand the system, and being able to, to be able to see the system can help us, okay, what am I working with? What do I have so that I can begin to apply the correct surfactant to the system? Okay, moving to the second variable that surfactants target is wettability. The way that we measure wettability is through a mechanism that we call contact angle. I really love this image here because it is a great visual on what exactly is wettability. What does it actually look like? So on the left side here, we have a water wet system. Here in the green, we have the oil. We have a water droplet here in the blue, and we have our rock surface. On the right-hand side, we have water droplet, and the solid rock surface. But I love how on the left-hand side, if it's a water wet system, the water droplet, what it wants to do, it's naturally attracted to the rock surface. It wants to spread itself out on the rock surface. And then we measure this angle, and that's a quantifiable number that says, hey, this is a water wet system. But I really love this slide here because it's a visual of what does it look like to be water wet. My water droplet here wants to be spread out on the rock and stay attached to the rock surface. Then moving over to the right-hand side, we have the same thing. We have a water droplet, but because it's an oil wet system, look how the shape of the water droplet is different. It now is kind of curved a little, and you can kind of tell that if you applied some sort of force to it, it would much more likely come up off the face of the rock than your left-hand side water droplet. And again, we measure that angle, and that quantifies us, hey, this is an oil wet system. Okay, so that's contact angle. Now moving into these images down below, we have this is an in situ image. So we have our grains here in the white, we have the oil here in the green, and then this blue part is the water. And again, really focusing on the visual part of look at the shape that the water, this point right here between the oil and the water, the shape is kind of a concave shape, and the water wants to spread out on the rock. This dark blue portion here is to describe that it's a water wet system. Then as you move over to an oil wet system, look how the shape of the water changes. And so it doesn't want to stick to the face of the rock quite as well. It doesn't mean it can't stick, but it doesn't want to stay there quite as easily. And you can see how the shape is different. And so this is just a visual of what your in situ reservoir might look like. Okay, so now moving into what exactly does wettability alteration mean? What exactly is it doing? Okay, I love this example because I think it's so simple and probably every single person is familiar with it. When you're at home washing your dishes, you put some soap on your dishes, and that soap helps lift the grease or the oil off the face of your plate. That is exactly what surfactants can also do and do for our reservoirs. They are lifting the oil off the face of the rock that may not be produced otherwise. You might be able to scrub really hard on your plate in your kitchen and you just can't get the grease off. But when you add a little soap, all of a sudden that grease comes off your plate. And in the same way in our reservoirs, we might do certain mechanical things in our reservoir to try to increase production, but eventually we're going to get to a point, which is what we're seeing in the industry, that we just can't get any more oil out. So what do? We've got to start doing something different, and customizing surfactants is one of those different mechanisms that we can do. So there's two things that surfactants do when it comes to wettability alteration. One of them is that it literally, the surfactant molecules will attach themselves to the oil right here like this. So the tail part is the part that's naturally attracted to the oil and literally lifts the oil off the face of the rock. The second thing that surfactants can potentially do when it comes to wettability alteration is that they will attach themselves to the interface and actually change. So just because I lift oil off the face of the oil doesn't necessarily mean that I change the wettability of that formation. Oil still might want to stick to that rock face, but surfactants, as they lay at the interface, can actually change the natural attraction of what is now attracted to the surface of the rock. So thereby changing it, which is kind of what this image here in the bottom left hand is trying to show, is that, hey, it's naturally oil wet, and as I apply a surfactant, it now becomes naturally water wet, and oil comes off the face of the rock. So how does changing wettability, lifting oil off the face of the rock, help us increase production? I've got a chart here on the right-hand side. On the x-axis, we have water saturation of your system. In the y-axis, we have relative perm of whatever liquid that you're looking at. So in this case, we have water and we have oil. So if we have a given water saturation for a system, and we're starting out, let's say we're in a carbonate reservoir, it is naturally oil wet. We're starting, let's say, somewhere here. And as we apply a surfactant, we then begin to move up this chart, and your relative perm of your oil begins to increase as you move towards a water wet system. The same goes for the water, the water of the system, right? If you have a naturally oil wet system, the relative perm of water might be pretty high if you have a naturally oil wet system. Now, as I begin to change the wettability of that formation, my water, the relative perm, can actually go down in the system. And in some cases, we're even seeing that if we apply a surfactant to a certain system, let's say that the oil production actually did not go up in a certain system, but the water production went down. That in some cases can be just as beneficial as the oil production going up. We may not want to produce it. Water can be expensive. We have to dispose of it. What do we do with it? There's all sorts of environmental concerns on what to do with water, right? So even decreasing water production, and maybe your oil production stays exactly the same, but if I can decrease that water production, maybe even that can be beneficial to these reservoirs. Now, one thing I want to point out here is that sometimes we think that if we just go to the extreme, we take it from the maximum oil wet all the way to the maximum water wet, that's exactly what we want. I'm going to be showing a couple charts in just a little bit, some lab experiments, that it isn't always what we want to just go from, oh, this reservoir is strongly oil wet, and I need to take to the maximum strongly water wet. Because if we think about it, if we go from strong oil wet to strong water wet, now my water may be immobile. It can't move. Now I might produce less water, but now you might be causing water blockage. And now the oil can't come out because it can't get around the water. So when we're designing these surfactants, we want to find a sweet spot that moves the oil, but also is not causing water blockage. And I think one of the challenging things that the industry has seen over the many years that we've used surfactants is that in some cases we've just gone to the extreme. We've tried to make it super water wet, but trying to find that sweet spot within a system can be extremely challenging. And that's really where the difficulty of and the importance of understanding our system and where do I want to take my wettability? How far do I need to take it to maximize production? And maybe in some cases, minimize water production. So finding that sweet spot can be extremely important depending on the system that you're working with and what you're trying to accomplish. Okay, this process here, if anyone has been working in a science or engineering field, should probably understands this process here, right? I've got to understand what I'm working with, okay? Understanding my rock, my mineralogy, okay? Is it water wet? Is it oil wet? What's going on with my rock? Understanding now the fluids that we're working with. I'm going to show you an example here in a little bit that just by changing the crude oil, you can potentially get different responses from the same exact surfactant. So I've got to understand my crude oil. And then also understanding, we're going to look at an example of just changing the brine composition, the water. If I've got low TDS or high TDS, total dissolved solids, is what TDS stands for. What kind of system do I have? And just changing one variable can change, what we're seeing can change the outcome of a surfactant. And I think that's another great example. We change, in our lab tests, we make one variable change, and we see that the same surfactant doesn't respond the same. If we take that thought and apply it now to our reservoirs, when we're working with reservoirs all over the place, different parts of whatever country you're working in, even the same formation, different parts of your formation can have different variables. All of a sudden you change one variable like the water or the crude, and now all of a sudden that surfactant doesn't work. And so no wonder why the industry worked itself into not believing in surfactants, because one company over here, they used a surfactant and it worked great. And so company in another part of the country, maybe even the same formation, but somewhere else, their variables are a little bit different. They pump that surfactant and they're like, I didn't see anything. That's a waste of money. I'm not pumping that. I don't believe in surfactants. And then maybe even worst case, they pump a surfactant and they saw that that surfactant actually hurt my well. Well, no wonder why someone's like, surfactants are terrible. I'm never pumping a surfactant again. They don't work at all. Well, company A, it worked in his system, but company B, it's like, oh, I didn't see any difference. And then company C is like, no way, we never pump that stuff. That stuff is damaging to the formation. How well did each of those companies understand the system? And not just the system, then understand the surfactant that they're working with. So once you understand your system, then you've got to understand your surfactants. What does your surfactant do? We looked earlier that there's thousands of different types of surfactants, and they can be lumped into 4 different big categories. Okay, what am I working with? What am I targeting? Am I trying to target interfacial tension? Am I targeting wettability alteration? Am I targeting both? Why would I target one over the other? Have we thought about those questions when we went to go pump a surfactant? A lot of times we find ourselves in a situation that we're doing what someone else did in a different reservoir, and we don't even ask the question, why am I pumping this chemical? oh, well, they pumped it over there and it worked. Well, it may not work over in my formation. So those are questions that the industry really needs to start understanding to maximize the effectiveness of these products. So then once we select a surfactant, a group of surfactants, we think that, hey, these ones will likely perform the best, then we take it to a lab environment and we want to test them. And I'm going to show you some examples here of tests and how these tests can help us identify the top performing surfactants. Our favorite test is the spontaneous imbibition. We love this test, and I'm going to break down how this test works for those of you that aren't familiar with this test. But we really like this test. There's other tests that people are doing, but this is our favorite test. There's also even a more sophisticated test called core flooding. But sometimes core flooding can be cost prohibitive. It can be more on the expensive side, and it can also take a long time. And so that's probably, some of you may not even, they're like, oh, we've done one core test in my entire career, right? Because it's expensive, it takes a long time. It can give you valuable information, but it's expensive and it can take a long time. And that's really the reason that we love spontaneous imbibition. Once we do our due diligence in the lab, then we take the product out to the field, we test it, we see how it works, and then we're doing a continuous improvement of this entire process so that we can constantly keep learning, keep growing in our understanding of our systems and our chemicals that we're applying. Okay, so here is a breakdown of the spontaneous imbibition test. For those of you that are unfamiliar with this, will hopefully you'll be able to grasp how this test works. So what we do is we want to take a clean core. We don't want a dirty core. We don't want it filled with drilling mud. We don't want it filled with a bunch of precipitates, a bunch of salt dried out. We need a core that is clean. And if it's clean, then it's going to be water wet. So this is what we're going to start with at first. We will take this core and then we will then saturate it with the crude oil from the system that we're trying to understand. So we actually take crude samples from customers and we saturate the core, with that kind of crude oil. But it's still water wet at this point. We then apply heat and time, and that process will then change the wettability of the core from water wet to oil wet. And we often call this an aged core because we're trying to make it representative of the reservoir systems that we're actually working with. So then we take this aged core and we put it in this device called an amide cell. And it's shaped like this, it's made of glass. We put it inside here, and in this blue part is the water that we're working with. Again, we need to understand the water that we're working with in our system, whether that's formation water or even injection water, plus surfactant. So in here in the bulk will be the water plus surfactant, or in some cases, you may not have any surfactant because you want to test what happens if I don't use any surfactants. As the surfactant starts to do its thing, starts to change the wettability, it starts to lift oil droplets off the face of the core. Those oil droplets begin to come out, and because oil is lighter than water, it will float up to the top here, and then we can measure how much oil came out of this core with this type of surfactant. We'll do that across several types of surfactants, and then we'll generate a chart that looks something very similar to this, percent oil recovery on the y-axis over time. And then we can decide, hey, this surfactant worked the best in the lab. Let's try that one in the field. Okay, so now I want to really share with you guys some lab testing that we've been able to do. This here are samples from the Middle Bakken in North Dakota here in the United States. And we have crude oil that is from the Middle Bakken. Our mineralogy is a mixed mineralogy that we're working with. So that's somewhere in between a carbonate and a sandstone, which often is a lot of the formations that people are working with. This chart here on the left-hand side, we actually used fresh water, so a 700 TDS. And where to start your eyes here is, let me get my mouse over there. There we go. It's kind of hard to see, but this orange dash line is the blank, which means all it was 700 TDS water in that amide cell. Okay, so this was what you might call the natural spontaneous imbibition of just water, which is what many of us are doing. And sometimes people pump just water and they're like, hey, we got an increase in production. Well, water will imbibe into your rock. It will do that. But then we have a couple surfactants here that did better than the brine. We have product B and product E that did better than brine. But then the other thing that I really want to point out here, why some people draw conclusions after their own experience with surfactants, is that look at these two products here. They actually were worse than just pumping water. And so this is great information for us as an industry to understand how we often have developed a negative response to chemicals that, like, oh, those don't work, or those hurt my formation. And in some cases they do. That's exactly what this test is showing us, that these two products here could actually hurt your formation. And one of the ways it could have been doing that was that it was going too far, possibly to water wet. It was moving too far across that spectrum and causing too much immobile water, causing water blockage. Okay, so this has really, for us, just been very insightful to understanding that not every surfactant is going to respond the same way in a given system. Okay, so now moving here to the right, this is the same exact system, but now the only thing that we changed is we moved to a produced water system, 70,000 TDS. Again, still crude oil from the Middle Bakken, same exact well, mixed mineralogy. And here now you can see that we got a different ranking of the top 4 chemicals. So over here with freshwater, B and E did really well. They did better than the blank. But over here, B and E did about the same as blank. Whereas on the left-hand side with freshwater products C and F, they actually perform better with a high TDS brine. Again, products A and D continue to underperform in this system. So really just changing one variable helps us see that the same surfactant could respond differently. And maybe if I change one variable, it's like, hey, I didn't see any change. Well, maybe that's why, because one variable changed, and now I'm unable to see that this product didn't any benefit to my reservoir. Okay, so here is a couple of examples that we here at Alchemy Sciences have had the opportunity to test. These are maybe some more familiarity with many of you. This is the Vaca Muerta formation. So the variable that was, so this is the Vaca Muerta formation. Again, we're working with a mixed mineralogy. In this case, we have fresh water on both tests. But in this test, the one variable that we changed was the customer. And these wells are about 100, I believe 180 kilometers apart from one another. Okay, so a good amount of distance, still in the same formation, but not necessarily in the same area. Now on the left-hand side, you can see that all of the products performed well. They all performed better. Here, this orange dash line again is the blank, and all the products outperformed the blank. Product C ended up doing the best. Now moving over to the right-hand chart, customer 2, the only thing we changed was the crude oil. That's all we changed. Again, here you have your orange dash line, which is your blank. All these products again performed well, better than the blank, but we had a slightly different ranking. Right here in this test, product B did better than this test over here on the left-hand side, product C. So this tells us that there are some variables just within the crude oil that can change how a surfactant could interact with that system. Again, emphasizing we have got to understand the system. We've got to understand our surfactants in order to be able to apply the correct one, or the one that's going to give us the best chance of increased production. Okay, so now moving to some field example. This is a case study that we did again in the North Dakota, an operator that we worked with. So this example was on 4 different wells. So well A is right here, this green line right here. Well B right here, these are all horizontal laterals. Okay, about 2, looks like they're 2 miles long. Well C right here. And then well D is actually up here. Right there. So these were the 4 wells that we tested. The only well that had surfactant in it, our product, which was well A. Only one of the wells. All the other 3 wells had no product at all. No surfactant product. Over on the left-hand side is the production response from those 4 wells. So on the x-axis, we have days. And on the y-axis, we have cum oil percent. And you can see here that the product was able to increase production in that well. And that's exactly what we're trying to accomplish. We were able to understand the system, understand the surfactants, the available surfactants, and okay, what surfactant should be applied in this situation. And this is a great example of it impacting production, helping to increase production. Okay, so this next slide that I'm going to go to is probably my favorite slide in the whole presentation. It does a great job, just very simplistically, at showing we've got to understand the system. We've got to understand the type of surfactants that we're working with to be able to apply the right product. There are thousands of different kinds of shampoos. And if you're a guy, you're probably thinking, I use the cheapest bottle and I've used one bottle my entire life and my entire career, and that's all I need, right? I've got what, a little bit of hair here. But if there's any women in the audience, you probably can relate to this, that you probably have like 5 different bottles on the shelf right now that you might go through. I know my wife, she is extremely particulate about picking the right shampoo, and it's got to be the right shampoo at the right time, depending on what kind of hairdo that she wants or what she's done with her hair. Again, I love this. It's just to try to show us that we've got to understand the system. That allows us to, or then we've got to understand what we're working with, what kind of surfactants, what kind of chemicals that we're working with to apply to the system to get what you want. You want crazy hair, you want straight hair, you want curly hair, whatever you're working for. If you have hair at all, mine's short. I don't need a whole lot of products, but what do you need? So for those of you that are still awake, I've got a pop quiz for you. This might be an easy answer. You might be able to answer this really quickly. What kind of shampoo do I need to use today? Hopefully, I'm not sure if you can answer this, but maybe you can help me out, because I'm a little confused with the number of shampoos on the shelf. All right. Thank you very much for your time. I've got my email here, so you're more than welcome to reach out to me personally and ask questions at a later time. If you think of something later, please feel free to reach out to me. But we are going to take the opportunity to do some question and answers right now, and I believe Joe is going to get us kicked off with that. So Joe, if you want to start looking over the questions that people have asked and see where we can go from here.
Well, great. Thank you so much, Ross. Didn't think I was going to learn about shampoos today, but there's always room for learning. Quick comment on the two options for asking your questions. The Q&A function, those questions will only be seen by the moderators and the panelists, whereas the chat function goes out to everybody. So we have received several questions. Let me kick off. What are the key reservoir fluid characteristics that theoretically could give the surfactants a higher chance of success in unconventional reservoirs?
Key reservoir characteristics that could give surfactants a better chance of working positively. So again, I think it depends, right? It can depend on what kind of system that we're working with to identify what kind of surfactant we want to apply. There are generally, if we're surfactants in general, change wettability from oil wet to water wet. That's what most surfactants, or a lot of surfactants that are being applied in the reservoir, are doing. They change from oil wet to a water wet system. And so if we apply a surfactant into a water wet system, and we have a surfactant that is going to try to change the system from oil to water, it's already water wet. So we might apply a surfactant to a water wet system. You're likely not going to see real strong benefit in that system. So sandstones tend to be more on the water wet side, whereas carbonates are more on the oil wet side. And that's generally where surfactants are targeting, is changing from oil wet to water wet. So in general, if you have a more oil wet system, more often than not, you're going to see a better response of increased production when you apply surfactant.
Okay. Are there any companies widely using surfactants, not just for pilot tests, in the Permian and or Bakken region, and with what sort of results?
Of course, it varies from customer to customer, but there are some customers that they understand the value and the benefits of surfactants. And so there are some customers, depending on the region that you're working in, whether it's here in the United States, the Bakken, Permian, Eagle Ford. Also, it kind of relates to the previous question that was asked. If you're working with with generally a sandstone type reservoir that's already strongly water wet, with the understanding that most surfactants move the wettability from oil wet to water wet. If you have a strong, if your reservoir is a sandstone, then those operators are likely probably not utilizing surfactant to a great extent. Whereas operators that are in more of a carbonate reservoir, the Middle Bakken, the Eagle Ford, the DJ Basin, those reservoirs are generally more carbonate, which makes them more oil wet, which gives you a better opportunity to apply a surfactant to go from oil wet to water wet, thereby increasing your production.
Great. Regarding how does the AMOT cell results compare to real world conditions in the wells under higher pressures and temperatures?
Okay, so let me, so when it comes to actual, probably another way to ask this question is in relation to how do we translate lab results to field results, right? So I'm not going to tell you, let me just move back here to slide 13. I'm not going to tell you that, okay, if we do a test with your system and in the lab, it got, let's see, the one here on the left is about 42, 43% improved oil recovery. I'm not going to tell you that now if you apply this product B or product E, you're going to get 43% improved oil recovery out in the field. The actual variable or the actual value is not going to translate in the same way. One of the reasons is because in the lab environment is a very controlled environment, right? That's why we do it in the lab, because we have control over all the variables. When we move out to the field, there are a lot of variables that are not as much of, we don't have as much control over many of those variables as we do in the lab. And so it's really challenging. It really probably doesn't matter what you're testing. There are many things that you're going to test in the lab, and it's going to respond differently into the field. But what we do say is that if we can see an increase in production over a period of time, so for example, when we look at this case study here in the Middle Bakken, when we did the lab study, this is exactly what we showed. We showed that this product would increase production. Now, the actual value that we got in the lab was not translatable to the field, but it was translatable in a sense that applying this surfactant will give you more production than if you didn't apply surfactant at all. And so what we really try to focus on with the operators is that if you can increase your production incrementally to the point that it covers the economic cost to apply the surfactant, then that's beneficial to your reservoir, that's beneficial to your economics, that you were able to pay off what it cost and then some, right? And it may not always be this line here, we don't have further data, but these lines here might eventually match up, right? Over the course of time, however much time, they might eventually match up. But if you're able to increase production to the point that it paid for the economics of the product itself and then some, then overall that's beneficial.
Quick question: what's the x-axis there? Is that number of days or months?
Yeah, that's days on this x-axis here.
Mm-hmm. Okay. On On page 6, you'd mentioned the various types of surfactants, the non-ionic, anionic, cationic, and amphoteric. What do you take into account when you're selecting which ones to use?
So basically, we want to understand the system, and if there's going to be a negative reaction between a surfactant that you're considering that might be applied to the system, then we try to stay away from those. So here's an example just from an application standpoint. There many friction reducers that are being used during frac jobs today do not interact well with a cationic surfactant. And so just from a design perspective, we're like, well, we know that they're pumping friction reducer, therefore we cannot use an anionic. So it's not only just understanding the system that you're working with, you also need to understand what else are you injecting into the formation, that can I use this surfactant or this surfactant over here.
Okay. For your surfactant injection design, what % concentration and how long do you leave the how long do you leave the surfactant injected in each well?
So the % concentration can vary from system to system. That can even be one of the variables that we can test for. Let me move to this chart here. The concentration can be one of the variables that we test for. We do see that concentration can play a factor. So actually, if you move back to probably this chart here, when it comes to IFT, adding too high of a concentration doesn't necessarily benefit us if we're down here on this plateau area. And so understanding where the CMC is within our system can help us identify how much concentration to add. In general, we're not adding tens of thousands of gallons, right? It's more of like on the range of 1 gallon per thousand, 2 gallons per thousand, half gallon per thousand. Somewhere in that range is kind of where most people are designing their surfactants for a given system. I think the second question was, how long do you apply a surfactant? Now this can be eventually surfactants are going to be in some ways used up, right? They're going to be either it all got produced over a certain period of time, all the surfactant ended up coming out of the reservoir. And so we actually believe that continual usage of surfactants can benefit the life of a well. Now, the frequency, I don't necessarily know the frequency. That can probably depend on the type of reservoir that you're working with, the operator, what they're trying to achieve. But there's a pretty big body of literature within water flooding. Surfactants have been used for quite some time in water flooding, and they're doing continual injection of surfactants in those applications. And so I think similarly, we can start to apply similar techniques that the conventional groups have been applying. We can start to do those things in the unconventional reservoirs that we haven't done. We're applying the surfactant continuously over life of a well to just overall increase the production of the well.
Okay, I think you've answered a couple of these with that, because they relate to when is the optimal time to utilize the surfactant. Is it when fracking? Is it during peak production? Is it during the declination of the declining portion of the well?
Yeah. Actually, if I could speak to that a little bit. So surfactants, because of what they're doing, right? They're changing wettability, they're decreasing IFT. Whether it's a new well or an old well, surfactants can be applied in more or less at any point in time in the life of a well, right? If you've been producing a well for a long time, and then, hey, let's see if we can get additional. We still believe there's a certain amount of oil still in place, and we think we can get additional oil out. We're actually working with several customers now that they're very old reservoirs, been producing for a long time, 20 plus years. These reservoirs have been producing, and we're doing some testing for them and seeing what surfactant in this environment would work the best to just get a little bit more oil out. And so whether it's an old reservoir, an old well, or even a new well, I think surfactants can be beneficial being applied across the whole spectrum of time in the life of a well.
What information is needed to run a lab analysis, and how long do those processes take?
Yeah, great question. So the main things that we need to do our testing is that we need to understand the mineralogy that you're working with. We don't need actual core samples, but we need to understand the mineralogy. So an XRD analysis can help with identifying the mineralogy of your system. We do want physical samples of crude oil in our lab. And then when it comes to brine, we don't need physical samples. We can just get a water analysis, and then we can make a synthetic brine in the lab. And then those are the three variables that we're going to get from your formation to then be able to run our tests. From a timing perspective, they generally take anywhere from 2 to 3 months to identify and to customize a surfactant for a system.
Good. Could you talk about how product is injected in the field? Is there particular equipment that's necessary? How long would I need to have the well shut in for that?
Right. Okay. Yeah. So if it's a new well, if the well's going to be fracture stimulated, then during that process, you can inject the surfactant. So if you've got you've got your pumps that are injecting the water, then a lot of times you're going to have a chemical pump that's going to be injecting the surfactant. So you're going to have a smaller type pump that's pumping the chemical. So you need some pumps of some nature, and then you basically need that same type of equipment if you're even in an older well. If you're doing a smaller injection, you need some sort of water pump, some sort of chemical pump. If you're doing a small injection, you don't necessarily have to have a chemical pump. You could batch mix the chemical into the water, and then the process just depends on how much water you want to inject, what kind of rate you want to inject. Depends on will dictate how long that takes.
And for a producing well, do you use coil tubing?
Say that again.
Do you use coil tubing for that injection?
Oh, you can, absolutely. You don't have to. You don't have to have coil tubing, but coil tubing is more of a mechanical mechanism to pinpoint where you want the fluid to go to. So if you're working with an old well, let's say an old horizontal well that's 2 miles long, right? So now you've got perforations all up and down your lateral. If you come back into that and inject water into that old well, it's pretty well understood that most of your water is going to go into the heel portion, let's just say the lower half portion of your lateral. That's pretty well understood within the industry and pretty well accepted. That's just what's going to happen, because that's where most of your production is going to take place, And so that's where most of your depletion is. And so that's where water wants to take the path of least resistance, and that's where it's going to go. So if there's an operator that wants to make sure that they get that chemical into a larger portion of the lateral, then utilizing coil tubing, packers, absolutely, that can definitely be a mechanical mechanism to help get the chemical into greater parts of the lateral.
Okay, and you've already somewhat covered the all versus unconventional reservoirs when you're designing your process.
Okay, so there was a little bit of a breakup there. Can you repeat that question, Joe?
Differences and considerations between conventional and unconventional reservoirs when you're designing your process.
Designing our process. Yeah, I think it's more or less similar to what we've been talking about this hour, right? We need to understand the system, understand what we're working with. Are we working with a carbonate sandstone? How long has the well been producing? That's really, when we say understand the system, what are we working with, right? If we've got a strongly oil wet system, you've got a better chance that the surfactant is going to work. If you've got a strongly water wet system, applying most of the surfactants, there are some surfactants that can work with water wet systems, but most surfactants work better with strongly oil wet systems. So again, whether it's an old well, a new well, and there's a large body of evidence that conventional reservoirs have been doing water floods, surfactant water floods, surfactant huff and puffs. The industry's been doing that for quite some time. And why are they using surfactants? Because they found that it's working, right? And so we're just trying to take the next step and do it even better than what we've been doing it before.
Okay. Having said that, surfactants do have an uneven record of performance in improving reservoir and well productivity.
Yep.
Why is that?
The variables that we work with there's a lot of variables that every reservoir has. And so I'm going to move to this chart here. Okay, this to me is a great example of trying to understand, why does surfactant A work in one formation, but I go to another formation and surfactant A didn't do anything for me. Then I go to a third formation and it actually caused a negative result. It made things worse, right? And so I think it's just been our lack of not fully understanding what we're working with and identifying that because there's so many different types of surfactants, realizing that it's not every surfactant responds the same in different systems. And so both these charts here represent that, okay, surfactants B and E worked in this system. For surfactants A and D did not. I change one variable, and now all of a sudden B and E, I see no change if I just pumped water. Right? And so as operators, a lot of times operators, they're just doing what their neighbor did, right? They're copying what their neighbor did. Hey, operator A over there, they pump this, let's go ahead and pump it too. It worked for them. Right? And so we're seeing that, so then it didn't work for you. And you're like, that was a waste of money. And so because unconventionals, the complexity of unconventionals is a degree greater, maybe even a magnitude greater than conventionals. And we're seeing that. We're getting so little oil out of these. And so because the complexity is so much greater, we've got to do a better job within the industry of understanding what we're working with so that I can say, okay, this is what I'm working with, and only products B and E are going to work here. And I move over to a different part of the formation, and okay, products C and E, C and F is what I need to would give me the best chance of success over here.
And along those lines, I think you more or less showed it there on your graph, but there's a question on the recovery factor improvement. What sort of a range might be expected? And I think you more or less talked about that there at the end.
Yeah, again, we're not going to be able to tell you that, okay, we saw 40% oil recovery in our lab test and say, okay, you pump this product out on your wells in your formation, even though the variables are similar, right? We tried to match your mineralogy, your water, your crude, that then to say, okay, you're going to get 40% increased production on your wells. There's so many more variables out in real life that causes the actual value to not be exactly the same, right? I'm not going to get 40% improvement out in the field just because I saw it in the lab. Now, with that said, we have seen up to 25% improvement out in the field, but that doesn't necessarily say the lab test didn't show 25%, right? That value, we can't trust we shouldn't put so much emphasis on the value itself. Oh, hey, showed 40% here in the lab test. That's what I'm going to get. And I go tell my boss, let's go ahead and pump this product because it's going to get 40%. And then you don't get 40%, right? That's the other thing that I think the industry has been challenged with, is that we expect 40% because we saw it in the lab. So I take it out to the field and I only saw 15% improvement. And so now we look at that and we say, oh, that was a failure. Well, was it? Okay, it might have been a failure when you compare it to a lab test, but if you got 15% improvement over an offset well or a well that you pumped zero product, that to me is a success. And so we have to get ourselves out of the mindset that, oh, whatever I see in the lab, it's exactly going to be the same when I move out to the field. The complexity is so much greater out in the field. There is so many variables that can change the values, the actual number of recovery that I get out in the field compared to a controlled environment in the lab.
Okay, how does salinity affect when formulating an EOR fluid containing surfactants?
Okay, so this chart right here, slide 13. I mean, this right here, the only variable that we changed was salinity. And so it absolutely can impact the way surfactants respond. Absolutely. So understanding what the salinity is, what you're working with, absolutely can change your results.
Okay, I think we're done with the questions.
Okay.
Ross, this has been a great session. Thank you so much. Those participants who are still with us, who seem to be just about everybody, thank you so much for participating. You have Ross's email. We'll be sending you also a PDF version of the presentation, so you can have that, as well as a link to the recording. So thank you all for participating in today's session. Please follow us on LinkedIn, become a sponsor, join us as a member, and we will see you next time. Ross, thank you so much.
Joe, thank you very much for allowing me to be here. I appreciated the time, appreciated all the questions from everyone. And if anyone has any questions, feel free to email me at a later time.
We'll do it. Mariano, muchas gracias.
Adios.
Goodbye, everybody. Ciao.
Hi, thank you, everyone.